So this is part one of our Finding the Best Fit Line development. You can be looking at classwork pages 82, 83, where we're finding the equation of the least squares best fit line passing through these given 5 points. Here what the 5 points look like: 2, 3, 3, 5, 4, 6, 5, 7, and 6, 9. We're trying to find the line of best fit, and what does that mean? We want to try to find a slope and a y-intercept such that the sum of the squares of the vertical distance has been minimized. So when we talk about best fit line, what is this sum of the squares of the vertical distances? Here are our 5 points again, and here's just some line which I can move up and down. Now notice each point has a vertical distance to the line, vertical distance, which when I square it and add it would be the sum of the squares of these squares here. And so this square here represents the sum of all the areas of these squares here. So for example, when I have a slope of 1 and a y-intercept of 1, that the distance, vertical distance from this point to the line is 0, the vertical distance here is 1, 1, 1, and 2. So if I do 1 squared plus 1 squared plus 1 squared plus 2 squared, that's going to be 4, 5, 6, 7, a total area of 7. Now program FIT will do this work for us automatically by taking the line with a given slope. So it asks for a given slope. If you put in a 1 and then a y-intercept of 1, it'll calculate that sum of the squares of the vertical distances as 7, as I just did. If you give it the slope of 1 and a y-intercept of 2, then the sum of the squares of the vertical distances ends up being just 2, because this vertical distance is 1, this is 0, 0, 0, and 1 plus 1 makes 2. When the sum of the squares of the vertical distances is 3, then, when the y-intercept is 3, then the sum of the squares of the vertical distances is back to 7, and when the y-intercept is 4, then the sum of the squares of the vertical distances is 22. When you plot those points, they will always form a perfect parabola, a y equals ax squared plus bx plus c equation. No matter which y-intercepts you pick, when you calculate the sum of the squares of the vertical distances, there's always one parabola that fits all of that data. So therefore, it doesn't matter what y-intercepts we feed program FIT. It'll just calculate the sum of the squares of the vertical distances and put these numbers into list 4 and these numbers into list 5. Because a perfect parabola fits this, if we run program QUADFIT, QUADFIT will give us the a, b, and c values that form this equation here. Now, we can actually see from this graph that the vertex point, the lowest point on this graph, is at 2, 2. But if we don't see that from the graph, we just do our negative b over 2a shortcut to find the x-coordinate of the vertex. And again, you can see that is 2. You need to understand that that 2 is the x-coordinate here. It represents the y-intercept that minimizes the sum of the squares of the vertical distances when the slope is 1. So that means that the best fit line with a slope of 1 is y equals 1x plus that y-intercept we just found of 2. Now, if we choose a different slope, say we choose a slope of 2, and we slide that line up and down, the y-intercept that minimizes that would be negative 2. Again, we could run FIT and QUADFIT to find that y-intercept of negative 2 for the slope of 2. And if we chose a slope of a half, then the y-intercept would be 4. No matter what slope we pick, there's a y-intercept that will minimize the sum of the squares of the vertical distances, and every single one of those lines passes through the same point. So we did that classwork where we found all the different lines of best fit pass through that fixed point, which we call the center of gravity. And instead of having to find best fit line, best fit line, best fit line, find their intersections, the easy way to find the center of gravity is to take the average of the x-coordinates, take the average of the y-coordinates. And that point 4, 6 is our center of gravity for our data set. And that is the end of part 1.